Hello, my name is Lori Bedbedian, and today we're going to be talking about ordinal regression models for continuous Y. This is what my final project paper was on. Ordinal regression models are used to predict the probability of an ordinal outcome. It's commonly used in healthcare research. These models are valuable for understanding the relationship between different factors and the likelihood of specific health outcomes. Today I'll talk about the introduction to ordinal regression, minimum sample size requirements, comparison of assumptions of various models, provide some data sets and descriptive statistics and how those look when applying these methods, importance of continuous response models, two algorithms, ACE and the AVAS function, a case study on transform both side regression methods, estimation of population mean and median, the use of arg.boot for testing effects of predictors, visualizations of predicted median and median Y, challenges with heavy ties and quantile estimation, and finally, concluding remarks and recommendation. The accuracy of estimates in ordinal regression models is influenced by the sample size, especially when estimating probabilities or quantiles. Understanding the minimum sample size requirements is therefore crucial for reliable results. This method is commonly used in healthcare research, where 0 is no pain and 10 is worse pain. The minimum sample size is important for getting reliable results. Here I'm showing a table which summarizes the minimum sample size and value of R squared that is necessary for a significant fit for the regression model, here with a power of at least 0.8, based on the given number of independent variables and value of alpha. Here we're comparing assumptions of various models, the parametric versus semi-parametric model. Different models have varying assumptions and precision levels. Understanding the comparison of these assumptions helps in selecting the most suitable model for the research context. Quantile regression makes the fewest left-hand side model assumptions, except for the assumption that Y be continuous. But it can have less estimator precision than other models and has lower power. To summarize how assumptions of parametric models compare to assumptions of semi-parametric ordinal models, we can consider some of the models and tests that we learned about this quarter. The ordinal linear model, or its special case, the equal variance two-sample t-test, versus the probit or logit ordinal model, or the Wilcoxon two-sample test. All assumptions of linear models other than independence of residuals are captured in the following, using the more standard Y is less than or equal to Y notation. On the other hand, as I'm showing here, the ordinal model assumes the following: assumptions of the linear model on the left panel and semi-parametric ordinal probit or logit in the right-hand side. Ordinal models do not assume any shape for the distribution of Y for a given xi. They only assume parallelism. The linear model can relax the parallelism assumption, but in practice, it is difficult to know how to vary it except for the unequal variance two-sample t-test. The data sets from National Health and Nutrition Examination Survey provide valuable insights into the associations between diabetes and mellitus type 2 and obesity. This type of diabetes I'll refer to just as DM type 2 is an adult onset diabetes, and it's strongly associated with obesity. Currently, the best laboratory test for diabetes measures HbA1c. It's also called hemoglobin A1c, and it reflects the average blood glucose for predicting 60 to 90 days. HbA1c is greater than or equal to 7. It's sometimes taken as a positive diagnosis of diabetes, even though there are no data to support the use of a threshold. And so the goal of this analysis is to better understand effects of body size measurements on risks of DM and to enhance screening for DM. Often the descriptive data sets used in these types of analyses look like this, where they're collecting different characteristic quantities from your blood. Continuous response models play a vital role in predicting this blood sugar level, offering advantages over binary logistic models. It is better to predict continuous HbA1c using a continuous response model. Then use the model to estimate the probability of that HbA1c level exceeds any cutoff or estimates the 0.9 quantile of the sugar blood level, thereby enhancing the diabetes screening. In this figure, we're looking at a downward trend in blood levels of glucose and levels of HbA1c decreases from 9.4% at baseline to 7.5% at the end of the observation period. However, glucose variability remained relatively unchanged from the first to the second month of observation, which results in 3 hypoglycemic episodes. They were registered by self-monitoring blood glucose at days 45, 48, and 55 in this figure, showing condition of the patient. Okay, so the 2 different types of algorithms that are utilizing this method are the alternating conditional expectations ACE algorithm and the additive and variance stabilizing function. They are powerful tools in the field of statistical modeling, particularly in non-parametric regression and ordinal regression analysis. They are primarily used for transforming data to achieve better model fit. So now to break these 2 things down, an ACE algorithm, alternating conditional expectations, finds transformations of predictor and response variables to maximize their correlation, allowing for modeling of complex nonlinear relationships. It iteratively updates these transformations until converging, enhancing the overall fit of the regression. However, the AVAS function, additive and variance stabilizing function, extends this ACE algorithm by also seeking transformations that stabilize the variance of residuals, addressing heteroscedasticity. It iteratively updates transformations to both enhance correlation and achieve homoscedasticity, improving model reliability and interpretation. And to transform both side regression methods, which is a case study putting ordinal regression with a continuous Y to test, and it's a technique used to enhance regression model fit. The main goals are to improve the linearity of relationships and stabilize the variance of the residuals. This method involves applying transformations to both the predictor variables and response variables. For example, using logarithmic or square root transformations, they can help linearize the relationship and handle heteroscedasticity. The benefits include improved model fit, better linearity, and more reliable model diagnostics. Here I'm showing 2 figures. On the left, we have the original data, which was a random data set I generated in Python to show the original data compared with a nonlinear relationship. On the right-hand plot, we have the transform data, which shows the data after applying a logarithmic transformation, resulting in a more linear relationship, indicated by the arrows in the right-hand plot, and then the regression lines fitted to both the original and transform data to highlight the improvement in linearity. The case study shows the practical applications of transform both side regression methods, providing insights into estimation of population mean and median. Here, we're showing the population mean and median, which are measurements of central tendency used in statistics. The mean is calculated by summing all data points and dividing by the number of points, and it provides a central value for the data. However, it is sensitive to outliers, which can skew the mean significantly. The median is the middle value, as we all know, and it's ordered from least to greatest. It represents the central location of the data. Unlike the mean, the median is more robust to outliers, making it a better measure for skewed distributions, as it provides a more accurate central value. Here I'm showing 2 histograms. On the left, a symmetric distribution or a normal distribution showing the calculation of the mean. And then on the right is a skewed distribution showing the calculation of the median. On the left-hand side histogram, the marker indicates the mean average of the data, and on the right-hand side, the marker indicates the median middle value of the data. Now we'll talk about the use of arg.boot function, which is used to test effects of predictors in the regression models. The preliminary purpose of this function is to assess the stability of predictors and effects and provide confidence intervals using bootstrapping methods. The method involves fitting an additive regression model, performing bootstrap sampling to estimate the variability of predictor effects, and generating confidence intervals and p-values. This approach is robust to model assumptions and provide a more accurate estimate of predictor effects. Understanding the representation of true population values will further enhance the interpretation of your results. The graph here includes the blue lines are regression, showing the predicted values as a function of the predictor variable. The green dashed line shows the predicted median Y value, and the red dashed line is the predicted mean Y value. The black dots are the data points generated in Python. Okay, Lastly, we'll talk about the challenges with heavy ties in quantile estimation. Heavy ties in quantile estimation can significantly affect the accuracy of our results. In this plot, where on the y-axis we have the response variable, and on the x-axis we have the predictor variable. The cluster of points represent areas where heavy ties occur, indicating multiple data points with the same value. And so this is one of the challenges we experience. It can lead to inaccuracies in your results. It's important to address these challenges with finding better fit model for your data. In conclusion, regression models for continuous Y and ordinal regression, including transform both sides regression, offer powerful tools for complex data analysis, often used in healthcare research. Recommendations for future research include careful model selection and transformation application and validation for model assumptions. Thanks for your attention. Hello, my name is Lori Bedbedian.
All right, thank you. So this is the first presentation from Lori, and our second presentation will be from Chenxi. So when you're ready, please share your screen, Chenxi. And you may start. We cannot hear you, Chenxi.
Can you hear me now?
Yes.
Okay. Can you see my screen?
Yes, we can see very well.
Okay, so my presentation is about missing data. I will talk about the commonly used methods and strategies for missing data problem and the different assumptions and scenarios in my presentation. This is a brief overview of my talk. I will first give an introduction to the missing data mechanism theory, and I will introduce three approaches to missing data problem. They are deletion, imputation, and model-based likelihood method. And I will mostly talk about imputation methods. Firstly, we have to understand the missing data mechanism. Let Y be the data matrix and R be the indicator matrix that indicate the missing data mechanism. We have three classes of missing data mechanism. The first is called missing completely at random, MCAR. That means the probability of missing is the same for all cases. R is independent of Y. And the second class is called missing at random. That means the probability of being missing is the same only within the groups defined by the observed data. That is, given Y observed, R is independent of Y miss. For example, in a survey for personal income, the females are less likely to answer in general. And the third class is called missing not at random. That means the probability of missing varies for reasons that are unknown to us. For example, in a survey, the participants with lower income levels are less likely to answer, but there is no way for us to know that. Most of the modern missing data methods start from the MAR assumptions. So here comes the first approach to missing data. It is simply deletion. We have listwise deletion and pairwise deletion. As the graph will illustrate, I will go through details of this method. It is very convenient and simple, but the deletion method is only valid for MCR missing data, so it is not so useful in practice. The second approach to missing data is called imputation. When I talk about imputation, there are actually two kinds of imputation, single and multiple. For single imputation, we replace a missing value by a single sensitivity value, and only one completed data set is created. But this is generally not true, as Rubin says, because we don't know what value to impute with certainty. If we did, it won't be missing, right? So we have multiple imputation. It tries to add some uncertainty to the imputation. In multiple imputation, a missing value is replaced by a set of synthetic values, and multiple completed data sets are created. And after that, the standard statistical analysis method could be applied in parallel to the completed data set and get the analysis result. The result from all the completed data set are combined for inference. This is ideal for multiple imputation. And here, I want to introduce the detailed algorithm for univariate missing data. Consider the most simple case, there's only one variable Y has missing data and other variable X are fully observed. We denote Y and X accordingly. We can do conditional mean imputation, but it's only effective if Y is independent of X. So we can also do conditional mean imputation or regression-based models. We can feed a GOM based on the observed value of X observed and Y observed to get the parameter estimate. And then we can use Y miss to predict the value of missing Y miss hat, to get a single imputed value of Y miss. But remember, just as I mentioned, single imputation is very dangerous in general. Imagine the world of simulation where we have access to both the true and imputed values. The natural question is, can we evaluate an imputation model by how well it can recreate the true data, that is in terms of the lowest RMSE? The answer is no, because the best method yielding the lowest RMSE is generally bad for imputation. It will find the same imputed values over and over again and ignore the inherent uncertainty of the missing value. So imputation is not prediction. In regression-based models, the single imputation is too good to be true because it will artificially strengthen the relation in the data. So we do multiple imputation by adding some uncertainty to the imputed values. And our level of confidence is on a particular value is expressed as a variation across the completed data set. In this sense, imputation is more like an inference problem. Okay, so this is a procedure for we do multiple indication in regression-based models. Assume a linear regression model is fitted, and if we only have one single predicted value, this is single imputation. But if we want to do multiple imputation, we have two choices. We can use predict plus noise. We plus noise to the predicted value of the imputed model, and noise can be sampling from the estimated Gaussian distribution or sampling with replacement from the empirical residuals. And secondly, we can even add some parameter uncertainty to the multiple imputation by sampling the parameter estimate from their posterior distribution. And the second method to deal with univariate missing data is called matching-based model. The idea is to match the missing Y miss to one or multiple similar observed Y observed. We call Y observed at donors. The procedure is like this. First, we specify a predicting model for Y on X and feed the model based on the observed value. And then we define a metric that can measure the similarity between Y miss and observed as the distance between their predicted value. And for each missingness Y miss I, we want to select a candidate donors by finding the D candidates that minimize the distance between the predicted value of Y miss and Y observed, and sample one out of them. This is a single imputation. But if we want to do multiple imputation, we can follow the same procedure as we mentioned in the regression-based models. We talked about the method for dealing with univariate missing data, but in practice, we might face multivariate missing data. That means multiple variables have missing data simultaneously, like the right graph illustrate. So here we introduce two methods to deal with this problem. They are joint modeling and fully conditional specification. The first method, joint modeling, we assume that the data matrix follow a multivariate normal distribution with parameter theta. Then the goal of this multiple imputation is to draw random sample from the group distribution, the joint distribution of theta, Y miss conditional on Y observed. But instead of drawing sample from the joint distribution, we want to iteratively join samples from the marginal distribution of Y miss and theta. In this case, MCMC algorithm is applied in two steps. We will iteratively join Y miss T and theta T in two steps until convergence. And the resulting Markov chain converging distribution to the joint distribution of theta and Y miss. And if we want to do multiple imputation, we can draw M such Y miss T from the Markov chain after its conversion. And the second approach to multivariate missing data is fully conditional specification. The idea is to impute the multivariate missing data on a variable by variable basis. Let Y be the variables with missingness and X be fully observed variables. The FCS specifies the multivariate distribution of Y and X through a set of conditional densities. Here, Yj is one variable with missing data. So the conditional density is the conditional density of Yj conditional on X and the rest column of Y. The imputation on the FCS is done by iterating over the conditionally specified imputation model for Yj. This is also an MCMC, but the convergence of this MCMC is not guaranteed because it is purely controlled by the users. It is controlled by the imputation model itself, so it is very flexible. Okay, so we've talked about deletion and imputation to deal with missing data. And the third approach to missing data is called model-based likelihood method. It is not so standard, but also very useful. It tries to model the missing data mechanism directly, then proceed to make a proper likelihood-based analysis. If we can specify a parametric model for the data and estimate the parameter directly for the model by MLE, then we are done. We have MLE for the incomplete data. We observe this is full information maximum likelihood. And we also have MLE for the complete data. This is called EM algorithm. I think I will not go through the detail of EM algorithm, but the idea is to we want to maximize the complete data likelihood through E step and M step. Yes, so finally to the summary and some practical considerations. There are 4 class of methods: deletion, single imputation, multiple imputation, and likelihood-based methods for dealing with missing data. A crude guideline: if the proportion of observation is less than 0.03, then we can simply use deletion or single imputation. Although they have some drawbacks, but it is not. But if the proportion of observation is greater than 0.03, then we have to use multiple imputation or model-based likelihood method when it is possible. And finally, I have 2 takeaways here. Firstly, I think the underlying reasons for missingness is more important than the quantity of missingness. And second, the perspective towards the missing data is more important than the methodology itself. Okay, thank you. That's all.
Thank you, Chenxing. I just have one quick question. So for the likelihood model-based likelihood method, what do they do imputation after they have the likelihood?
Actually, they got the parameter estimates.
Right, and then they stop there. They just will.
Yeah.
Yeah.
Yeah, I think the purpose is different because imputation try to find one value of Y miss hat.
Yeah.
I think the model-based likelihood just skip this part, but get the parameter estimates directly.
I see. So the goal is just to do parameter estimation, not to get the data.
Yeah.
Okay, thank you, Chenxing. All right, that's very nice. And let's move on to our third group. I think Narine and Vibe have, if I pronounce it correctly, the names. Are they there? Narine.
Hello, Professor.
Yes.
My teammate has emailed you saying that he's stuck in traffic, like he was on campus, so
Okay.
he's running a bit late. So do you want me to present my part, or do you want both of us to present at the end?
So you will split the presentation. You will each present a part.
Yeah, so what we were thinking of was
So
presenting.
if he has to present, then we should wait for him. That we should postpone your presentation after he comes.
Okay, sure. Thank
Yeah, okay. All right, so then let's move on to our next group, Hao Yang and Zheng Tong.
Yeah.
Thank you.
Yeah.
Okay, so our group will present on the chapter 2 of the textbook, which is sort of a general overview of fitting regression models, and we'll talk about maybe a few problems that the book used to address certain problems when fitting a model. So next slide, please. So this should be a slide that everyone is familiar with. It just gives you like the general formulation of a regression model where you can have a link function and you're basically predicting the like relation between X and Y by like a coefficient beta. So next slide, please. So when like making model regression, we are interested in like the effect of XJs. So it is also an important problem about like how do we impose the predictors. So aside from like we see in homework, there's like discretizing variables. Like in homework 1 and 2, we were making like the numbers like 0, 1, and 2 based on the scale. There are a few other cases. Of the first one, we can add in an interaction term where like not only x1 and x2, but also they like put together can have an effect. A very like important example is when predicting maybe medical health parameters. we can have x1 as age, x2 as sex, and then adding an x1 times x2 term, meaning that sex and age combined together can also have an effect. The other example is a nonlinear term. So aside from a linear model, we can also have like a polynomial of x can also influence on y. So next slide, please. So because there are problems arising when determining predictor terms, we want to address them. So for example, in discretizing predictors, an example that the book mentioned and also like a few previous papers point out is that, for example, in last century, when like medical papers predict disease parameter cutoffs, it seems that people are just minimizing p-values. So they are finding the exact cutoff points where p-value are minimized. But like it actually turned out that these cutoff points don't actually have any medical meanings. So which means that when discretizing predictors, not only p-values, but also different circumstances based on the data set, we should take care of. And also, for example, in nonlinear terms, and in particular the polynomial terms we see previous slide, they can have undesirable peaks and valleys because we know polynomials oscillate a lot. And also high powers of one term can affect the fit of other terms. So next slide, please. So to address the problem that polynomial terms can oscillate a lot, the method the book proposes the splines. So they are used to divide intervals of x-axis into pieces. And we can see this is a demonstration of a linear spline. Basically, this is just like made up of piecewise linear functions. And by cutting x-axis into pieces, we can address the different behaviors of like different region of data using different models. So next slide, please. Although like linear splines are useful in many circumstances, they don't fit highly curved lines well. So the book proposed that in most circumstances, a cubic polynomial is enough for fitting most of the functions. And like the definition of cubic spline is basically just splines, but you adding like cubic terms. So next slide, please. But there are also problems with a cubic spline that actually they will oscillate a lot prior to the first cutoff point and after the last cutoff point. And these oscillations may not fit the behavior of the data very well. So people are like find out a solution that is to use the restricted cubic spline, which makes like the spline linear in tails and before the first cutoff points. With such definition, we can see that x can be linear after the last cutoff point. Next slide, please. So another question is how do we choose the knots? How do we choose the cutoff points? So in all previous slides, we were treating as if like we already know the A, B, C values are, but in practice, it might be up to us to choose the exact value. So, and also it's up to us to choose like how many cutoff points we actually want. So according to a paper by Stone in 1986, he like pointed out that the places where we place cutoff points doesn't really matter, but it's actually the number of knots k that like is more relevant to fitting the model. So in practice, people will place knots at fixed percentiles, but people might choose k. Like most time, k between 3, 4, and 5 fits most circumstances. If you have a really complicated model, then people might choose k up to 7. And in practice, people minimize like the Akakis information criterion to determine the number of knots k, which the AIC is based on like log likelihood. Next slide, please. Another like spline that the textbook didn't mention, but is also very useful, is the B-spline, named after the Bezier curves. They're more numerically stable, which means that they don't typically blow up, but they do not admit a linear term outside the range of T. so they don't have the good behavior of a restricted cubic spline. And we can see that the basis functions, the polynomials, are defined recursively, which means that it is also like more complicated to implement numerically. So these are like one aspect of addressing a like linear regression model. And Eric will talk more about non-parametric regression.
Yeah, thank you, Haoyang. So, like there are some like cases where we cannot specify the systematic structure of the model. So, for example, suppose we have a function of like this very complex form, where this is the first part is the systematic structure, and next part this is the random structure. We know the linear regression cannot fit this function well. For example, if I do the experiment in R, if I sample some points of this function, and I draw like a linear fitting curve in red, it's like we can see that this is not fitting well. And then as we learn from the class, we can also draw the residue plot and QQ plot. We can also see like the residue is not distributed randomly across the zero, and the QQ plot there are some like big tails. So how do we address this problem? So here comes like a non-parametric regression. So the idea is to use the moving least square, like we draw like a moving straight line to smooth the fitted curve. And here comes the lowest regression, which is the short for locally weighted regression. And the overall idea is to fit using a locally weighted least square. This weighted least square is the same as what we learned in class. And so in this way, we will actually put a higher weights for points in the neighborhood of the current point. This is like a k-nearest neighbor, or if you are familiar with the like CNN, it's like the kernel padding that put more higher weights to neighboring points. And the features of this lowest regression is that it smooths a fitted curve using an interpretable and statistical model. This is distinct from the neural network, which might not have like an interpretable interpretation, and it might not have like statistical power properties. And also it helps to downweight outliers for robustness. And this is like I try to replicate the lowest regression algorithm. So let's first focus on the first part. So we for each point, this is like a double loop. We construct the weight matrix, and for each term, we assign weights according to the distance to the current point. And then we have like a regression for this point. And then we actually predict this function value using this with the least square regression. And we do this for all data points. So after this, we will have something like this, like the crosses are the fitted value, and the red dots are the actual data points. But we notice that like some points are actually put up by these outliers. And a very simple solution to this might be like we see that if there's like a large residue gap, we can just inversely downweight the weight in the weight kernel. So that's actually the idea of the second step of lowest regression. So this is like a optional step, but it helps to ensure the robustness for further smoothing. So we first get the residue of prediction at each point, and then we do the clipping. Basically, we want to ensure that each value or each weight should be between -1 and 1. And then we use the inverse function. Basically, R here is the inverse to the E I star. And then we multiply this R with the previous W, so that the data points with large residue will be downweight. So this helps to control for the outliers. And after this second step, we can see that the curve is much more smoother than the previous point. So if I show the previous plot, we can see that this is not so smooth, and this is much smoother. And we also want to understand some like fitting parameters of lowest regression. The first parameter is alpha, which is between 0 and 1, and it means the weights of the sliding window. basically, if alpha is, for example, 0.5, we will use 50% of points in each regression at each point. So we see that if we use like more points or larger alpha, the curve will be smoother. The other like parameter is the degree of polynomial. Basically, I think this is very simple to understand. Basically, if a lambda is 2, we will include all the second order terms, for example, x1, x2, x1 square, and x2 square in the regression. So it basically it allows for more flexibility in the regression.
I don't know. Yeah, please plan to wrap up soon.
Oh yeah. This is my last slide. And also there are like some other types of non-parametric regression, like nearest neighbor and regression trees and kernel regression, and even neural networks. So I think in summary, if I want to link this non-parametric regression to our class, we still have a model where y equals y, fx equals plus epsilon, and epsilon is ID arrow with expectation to be 0. This is the random structure we learn, but there's no assumption on the systematic structure. So there's where non-parametric regression come into place. Okay, thanks.
Thank you very much, Zhengtong. This is great. Yeah, this is a very comprehensive review from Haoyang and Zhengtong. So now let's move on to our next presenter. Let me pull up the schedule. So it will be Yizhuo and Muzhi. Are you here?
Yeah, we are all here.
All right, please start your presentation if you're ready.
Okay, great. Let me first share screen. Okay, can you guys see my screen?
Not yet. Let me see. Yes,
Oh,
I
not
can
yet.
see. I can
Okay,
I
nice.
can see that. Yeah.
Okay. So everybody, hi everybody. We are going to talk about two methodology in survival analysis and their applications. So first, an overview of survival analysis. It is basically analyzing the expected duration of time until a particular event occurs. And such event can be death or like a failure in the mechanical systems. And the central concept of survival analysis, the survival function ST here, and it's a function of probability that a subject survives beyond time t. And the corresponding concept is the hazard function, which is the instantaneous rate at which events occur. You can take this as the how risky it is at time t. If you look at the formula, it basically means given that you have survived beyond time t, what's the probability that the failure may occur during this time interval delta t? And we take this delta t limit to 0, you have the instantaneous rate. And the relationship between the survival function and the hazard function is here as below. So that means as long as you have one of them, you can recover the other. And in real life, it is hard to know what's the real ST. So we have to find a way to find what's the an estimate for the survival function. And we'll introduce the Kaplan-Meier estimator, which is a way to to recover the S hat T. And it's a non-parametric statistic for estimating the survival function, which means there's no assumptions required for the structural form for the ST. And another advantage is that it can accommodate sensor data. So sensor data is sometimes you lose track of some of the subjects. For example, you have patients transferring to to another hospital and you lose track of them. And such things is very common in clinical studies. So that's why that's one of the reasons why Kaplan-Meier estimator is very popular in this area study. So first, we'll introduce some intuition for the KM estimator. So it's basically conditional probability. So let's say you want to find what's the probability of surviving longer than 30 days. So you just do it by the definition of conditional probability. You find the conditional probability of surviving longer than 30 days conditioning on you have survived for 12 days. Then you multiply by the marginal probability. And for the conditional probability, we'll calculate using this formula. So which means among all the individuals who have survived until time ti, what is the number of failure during this time? So it is at time ti, what's the failure rate? If you look at this formula, it's more straightforward. So the S hat T1. So until the first event, what's your survival rate? So D1 is the number of failures, and this is the total number. So this is the failure rate until survival rate until time T1. And then moving on, you want to compute the failure survival rate until time T2. You basically have this S hat T1 here, and you multiply by this conditional probability, and so on and so forth. You will get this KM estimator as a product of everything until T. So this is the end of the experiment or the clinical trial. And then we'll take a look at two case studies. One is about the breast cancer treatment. And the main goal of the study is to compare the effectiveness of various treatments for breast cancer. So they have randomly select participants and give them different treatment, and they want to know what is the disease-free survival rate for the different treatments. And they have used the Kaplan-Meier estimator and the log rank test, which compare the survival function for the two treatments. And this is what they have gotten for their result. If you look at the figure, on the y-axis is the survival function, which is the ST we have talked about. And the curve is downward sloping, which means as time goes by, the survival rate will drop. And if you compare the two slope here, so the blue line on top, which means the survival rate for the blue line is higher. So if you're using exemestane for the treatment, you have a higher survival rate. So the 5-year disease-free survival is 91% versus the 87%. So when you have this graph, it's very straightforward and clear to compare the survival rate. And another similar experiment we have here is for HIV treatment. And they want to compare two treatments. One is at early stage, the other is deferred ART treatment for HIV. And they want to compare like the overall survival rate as well. And they have used a similar estimator. However, for the result, they have a different form of presentation. Just now we have downward sloping curve, but this one we have like upward sloping, because we instead of survival function, we have the cumulated probability of mortality. So you have a upward sloping, and this figure also tells us you can compare the mortality rate between the two treatments, and the early treatment actually gives us a lower mortality rate between the two. So now we have talked about the strength and some case study about the KM estimator. We also cannot ignore their limitations. And one important limitation is that they do not account for different covariates such as gender, age, or like income groups. And now my teammate Muzhi will be talking about how we can use the Cox proportional hazard model to address such a limitation.
Okay, thanks, Yizhuo. So now let's move on to the Cox proportional hazards model. So first, equation 1 gives the hazard function of the Cox proportional hazard model. So here ht given x is the hazard function at time t given the covariates x. And the hazard function can be decomposed into two terms. The first one is h0t, which is the baseline hazard function. And it describes the hazard when all the covariates are 0. And the second term is the exponential term. So here, the x1 through xp are covariates, and beta are the coefficients. So in Cox proportional hazard model, we assume that the effect of the covariates on the hazard is constant over time, which is given by equation 2. And this is a key assumption of the Cox model, and we call it proportional hazards assumption. So next slide, please. Yeah. So now let's discuss how to estimate the model. Since the hazard function can be decomposed into two parts, we can estimate the h0t and beta separately. So first, to estimate h0t, we can just use the Kaplan-Meier estimator that Yizhuo has just talked about. And so our focus will be on the second part to estimate the effect beta. So the methodology we used is maximizing partial likelihood. So the partial likelihood function is the L beta given by equation 3. And now we're going to discuss how to derive this function. So first, we define the risk set. So RTI is the set of individuals still at risk just before time t and time ti. And here time ti is the time of the event or censoring for the ith individual. And next, we have our the conditional probability that the ith individual experiences the event at time ti, given there is at least one individual experiencing the event at ti. So this conditional probability is given on the left-hand side of equation 4. And by doing a simple algebra, we can get equation 5. And the partial likelihood function is the product of these conditional probabilities over all observed events, and which is L beta. And then we take the log of the partial likelihood function, and we get equation 6. So the final step is to maximize this log partial likelihood function over all beta, and then we can get an estimate for the coefficients. So because the Cox model is very useful in clinical study, we're going to introduce a case study in lung cancer staging here. So the goal of this study is to develop a staging system that classifies lung cancer patients into different stages based on some prognostic factors. And we have more than 5,000 lung cancer patients as participants. And the methodology is to use the Cox model to estimate the effects on survival rate of covariates such as age, sex, and tumor characteristics. And then we classify the lung cancer patients into 4 stages based on their covariate levels. And finally, we use KM survival curves to measure the performance of the staging system. So here are the results. So first, we find there are several significant predictors, including tumor size, lymph node involvement, and metastasis. And then we classify the patients into several stages based on their level of these predictors. And here the figure shows the KM survival curves of the patients for different stages. For example, for stage 1 patient, we can see the survival rate drops gradually in 5 years. And for stage 4 patients, we can see there's a sharp drop in survival rate in the first year. So this validates our new staging system. And finally is our conclusion.
Yeah, please plan to wrap up soon.
Yeah, this is the last slide. Yeah, so first we discussed Kaplan-Meier estimator. Due to its non-parametric nature, the KM estimator provides great flexibility in analysis. And also the KM estimator is useful in handling sensor data and comparing survival curves. And finally, we introduced Cox proportional hazard model, which can address the limitations of KM estimator by adding covariates into the model. So that's it for our presentation. Thank you.
Thank you very much. So my quick question is that for the baseline hazard function, are there alternatives to the KM estimate?
Yeah, I think so. But here, so for the baseline function, it does not assume any structural model, so you can use any model that you want, and Kaplan-Meier estimator is one of them. Yeah, but I think you can use the other as well.
Thank you. All right,
Yeah.
let's move on
Thanks.
to our next group. Thank you. Thank you for the very nice presentation. Tianqi and Yingshi.
Okay, can you see my screen?
Yes.
Okay, hello everyone. Our topic is actually very similar to what the previous group presented, but we focus more on the Cox model part, and we want to present on its application on social network modeling. So as the previous group have just covered, survival analysis is used to work with survival data or time to event data. Here is an example of survival data that describes time to divorce among a bunch of married couples. We can see the years of marriage for each couple, whether divorce is observed, and whether they are in couple counseling group. Our primary interest here is the time duration until divorce happens, and when event equals 0, that means divorce has not occurred. We call this observation censored. The couples who remain married to the end of the study will become right sensor data because their time to divorce is a unknown duration that's longer than the duration of observation. Now, with the data setup, let's introduce some basic concept. We've just heard about survival functions, which is the probability that the event doesn't happen until after a time t. And there's the hazard function, which is the instantaneous rate that the event will happen at time t. There are different assumptions about the shape of the baseline hazard function. And since the shape doesn't matter much for the Cox model, we can assume piecewise constant hazard function to simplify things. This is also another response to Jessica's question just now. And the Cox proportional hazard model is a semi-parametric version of the parametric proportional hazard function model. The Cox model is widely used precisely because of its semi-parametric nature that does not require any fitting of the underlying hazard functions and can handle right sensor data more effectively. The exponential form of predictor variables can help us to evaluate the relative risk given predictors values without worrying too much about the underlying distribution of lambda t. The Cox model is specified in a similar way to the parametric model. Lambda t given x equals lambda t multiplying the exponential of x beta, where x beta is a linear combination of predictor and their effects with no intercept term. The model assumes linearity and additivity of predictors, and it assumes no interaction terms between time and predictor. So the effect of predictor variables are assumed to be constant across time. To estimate beta in a Cox model, we do our usual trick of finding log likelihood function, but the likelihood here for Cox model is a partial likelihood among the uncensored observations. And this log partial likelihood function is assuming that there is no tied failure times in the data, which means that for the divorce example, there is no two couples divorcing at the same time, but this might not hold in reality. So when there are timed failure times, we can use Ephron's approximation to retrieve the log likelihood function. Once we get the log likelihood, we can use MLE estimation to find beta because the complexity of the Cox model, we can use the Newton-Raphson optimization that we learned in class to generate beta here. We can first find the gradient of the log likelihood and then the information matrix from the hashing of the log likelihood. And then via initialization, we can iterate through this Taylor expansion to find beta into convergence. And next, we want to introduce the powerful application of Cox model in social network studies.
Thank you, Christine. And before we go deeper, let's review some key features in social network. And instead of dealing with a single variables, the social network working with nodes and edges. Maybe you can mute yourself, Christine. Thank you. And the previous slides, you haven't finished. Thank you. And for example, in this example, there's a training program and we ask everyone if they have spoken with other scholars and indicate a name. And here each scholar is a node and a connection exists if there is a conversation. And we define a n by n adjacent matrix to store the data. And each row and column represent the actors and each cell in the matrix indicate whether a connection exists. And the picture shown here is a typical one-mode network and is often used to study actor-to-actor connections such as the conversation. And next slide. And another form is two-mode networks, also called bipartite networks. We usually use it to study actor-to-event connections. Unlike the one-mode networks, the bipartite networks have two separated node sets, set S and set Y, where connections can only be made between nodes from different sets. For example, in student course enrollment, student will not enroll other student, right? So then how can we study the similarity between student or between courses? We can actually create an one node network through projections. And here S1 is connected with S4 because both of them have a connection with Y1. Next, please. So like there are two interesting questions in network modeling. The first question is how individuals are influenced by their friends. And the second question is how long does it take for pairs of nodes to be connected? For the first question, imagine a scenario that your friends start playing online game and send you an invitation. We would like to join too. Let's say the ice bucket challenge. For me, even if all my friends participate, I would never join this game. So in this event, we consider the time the game is initiated as the starting point and the moment a user accepts the invitation to begin playing as the end point. And this process is actually very similar to the structure of survival data. So joining the game can be viewed as the point of death. And the event time we want to start here is the duration until a user accepts the invitation. And if a user never starts the game within our study period, it will be treated as censored. So here, the latent course model was proposed to help us to examine what characteristics make individuals more likely to be influenced by friends. The main differences between the new models and the traditional Harzer function are the incorporation of network structure and the additional binary latent variable susceptibility, which represent whether individuals will be influenced by their friends. And in other words, if individual I and individual J are friends, the probability of this person starting the game may also be influenced by the covariance of his or her friends. And the role parameters describe the magnitude of impact from friends. Next, please. And notice that if all beta coefficients are 0 or the adjacent matrix is a 0 matrix, the role parameter actually cannot be estimated because the inference of the parts, they already doesn't exist anymore. And to estimate the binary latent variable, the author used the logistic regression with the same covariance but added an intercept. And then the partial likelihood for uncensored data can be written in this way, and the delta indicate whether it is censored or not. And next, please. The second question we're interested in here is, in a social network, how long does it take to establish connection between nodes? And in the context of educational assessment, this question can be rephrased into how much time do students take to answer a question? For instance, for an exam with P binary scoring question and M exam is, the response matrix is actually a two-mode network. We can view the exam is and question as each node set. And if student K answer question I correctly, it represents a connection between these two nodes. And the time from seeing a question to providing an answer also similar to the structure of survival data. So here the event time is the information processing time of the exam E. And the main interest is to know the differences in response time between correct and incorrect answer. The proposed Bayesian latent space models try to solve this problem by first using latent space model for the network structure, that's to capture the adjacent matrix. And the latent space model assumes that the network connection can be explained by a shared D-dimensional latent space, and we have P latent precision ZK in the space and the question latent precision W subscript J. And then the conditional Harzer function can be expressed with the person latent traits, which can be interpreted as the speed of answering a question and the distance between person precision and the question precision in the latent space. Next, please. Also, the Harzer function is specified for two types of responses, the correct response and the incorrect response. And the Harzer function is very across different questions. So taken together, we can have the joy density for response accuracy and response time. And the model is estimated with Gibbs sample because the latent precision are actually not identifiable. So our presentation try to review how the course model can help in modeling the inference from friends and the time spent on the formation of the connections. So by directly using the adjacent matrix or using the latent space model. So I think both of these two models contain lots of fun and hope you all enjoyed it. Thank you.
Thank you. This is very interesting. I just want to ask whether people have considered a comparison between using the network adjacency matrix directly into the Cox model versus first embedding the network as a latent space into a latent space and then using the latent space embedding as the covariates in the Cox regression. Have you done any comparison of the two approaches?
As far as I know, there are no papers to compare them all. I think like using the addressing matrix and using the latent space matrix, they have different like
Assumption.
different purpose, I would say, because the latent space model is more likely to help us to visualize the network structure, try to visualize the dependencies among the set S and the set Y. Like if we just use the adjacency matrix directly, we cannot do this, I think. Yeah.
Whether you believe that the network is generated by some latent space, like factor model, I think that will be also the key difference, whether you have added an assumption, you have a network structure.
Yes.
Okay, thank you. Thank you very much. And we have the next Siyu and Hao Tian as the next presenter.
Okay, hello everyone. So today our presentation is about multivariable modeling strategies. So in this presentation, we will first introduce potential problems and then how to solve it, and then we will introduce some modeling strategies. So first, there are two potential problems when it comes to multivariable modeling. First is overfitting. So it happens when a statistical model captures the random fluctuations instead of the actual underlying assumptions between the variables. And how can we solve this? One of the potential solutions is limit the training size. So for example, studies have shown that a fitted regression model is more likely to be reliable if the number of predictors is less than a certain number. And the second problem is collinearity. It happens when at least one predictor in the regression model can be accurately predicted by other predictors. And scholars have used variance inflation factors to detect collinearity. And in the next section, we will introduce variable selections. And since this is a really large topic, we'll introduce 3 types of variable selections. We will introduce the advantages and disadvantages of each of them. So the first is the forward selection, like its name. So it starts with no variables, and then adding variables with those statistically significant until there's no remain. And the recommended stopping rule is the residual chi-square with the degrees of freedom equals to the number of candidates variable left at the current stage. So these methods have some advantages. For example, it starts with a simple model. So it's computationally efficient and easier to interpret. And also it is less affected by multicollinearity. But they also have disadvantage. So for example, adding a new variable in the model will make the previous or existing variable not significant. And once a variable is included, it will not be removed from the model. And next is backward elimination, and it is the most commonly used methods. It's contrary to the forward selection. It begins with all the models and then remove the least significant ones until only the statistically significant variable exists. And the advantage of backward elimination is that it generally outperforms forward selections. And the disadvantage is that once the variable is removed from the model, it cannot be considered for inclusion. And the third type of method is stepwise variable selections. And it integrates both forward selection and backward elimination. And the advantage of stepwise selection is that it's simple to use through statistical software, and it ensures no potential significant relationship are overlooked, and it ensures the reproducibility and validity of the model. However, it also has some disadvantages. For example, the inflation of R-square values, and it generates disproportionately small p-values, and that does not have substantive meaning. And also is susceptible to arbitrariness because of the collinearity. And in the next section, we introduce data reduction methods. And since also this is a really large topic, in this presentation, we'll focus on principal component analysis to reduce the dimensionality of the data. So the high-level concept of PCA is that it transforms a set of correlated variables into a new set of uncorrelated variables to reduce the dimensionality of the data. So each PC is independent of each other and is ranked based on the amount of variance it explains. So for example, the first component will capture more variation than second component, and second component will capture more variation than third component, and so on. And to maximize the variance, we need to calculate the first weight vector that can satisfy the first function. And then following the function, we can calculate the kth component as the second function here. And then you might ask, how much data reduction is necessary, right? And to answer this question, we can use the expected shrinkage to guide this process, and shown by function 2. And here we let LR to denote the log likelihood function chi-squared for this full model. So here we see the model chi-squared will be represented as LR here. So the first step is you calculate the gamma hat. And then if the gamma hat is smaller than 0.9, it means that, oh, we probably need to use this data reduction methods. And then we can calculate the target number of total regression degrees of freedom. And it needs to be smaller and equal to LR minus P divided by 9. And if we satisfy this condition, it means that the reduced model is expected to have less than 10% of shrinkage. And the final step is that for the reduced model to have acceptable calibration, the LR must be greater than P plus 9.
Is there any justification for this P plus 9?
I don't think so. It's I think we read this from the book, and I think this is more of a standard procedure according to the book.
I see. I think some justification should be added. If the book doesn't provide, you can look it up. So
Okay.
why would there be like a plus 9?
Okay.
Yeah, because for the less than 0.9, that sounds like 90%. People might think 90% is a big proportion. That's my interpretation, but this plus 9 seems to be not so straightforward.
Yeah.
Okay.
Thank you, Alice. So moving on, we'll talk about a overly influential observation and how to compare it to models. So we all know that like every observation impacts the fate of the model, but it will become problematic when a model is largely depends only a few highly influential data points. So here we discuss the common diagnoses for the overly influential points. The first is leverage, which measures the potential to be influential. The diagonal of the hat matrix is the leverage measure for the observation, which is not affected by Y. And a commonly recommended threshold for high leverage is 2p/n, which is twice the average leverage. It is also recommended using 3p/n as the cutoff for small number of observations. So now we will talk about like how to measure actual influences. So the first is the difference in fits or diffs. That is the differences in the fits upon removing observation I and standardized by the SE. A commonly recommended threshold is that if the absolute value of diffs is larger than 2 first p/n, that is we deem the observation to be overly influential. Similarly, you have the diff betas, which is the differences in the betas upon removing observation I and standardized by the SEs. So for that, a commonly recommended cutoff is 2 for small data sets or 2/√n. Lastly is the Cook's distance that we covered in lecture, which has the same philosophy as diff fits or diff betas, which is measures the changes in beta hat with or without observation I. A general rule of thumb is that if an observation with a Cook's distance larger than 1, it should be considered as having a extensive influence. So finally, we'll talk about like how to compare two models. So the intuition is that we cannot just simply choose a model that is like has a better performance. Prefer that we might just select a model with that's like overfitting data. So in comparing two predictive models, we often concern ourselves with calibration and discrimination. So calibration first, it measures how well the estimated prediction align with the observed outcomes. A simple assessment is just to plot y against hat y, and we can calculate the calibration intercept, which has the target value of 0 and the calibration slope. Another commonly used test is the Hosmer-Lemon-Shao test, which also assessment calibration, but it has some drawbacks and we don't recommend using that. And lastly, discrimination represents the ability of a model to correctly differentiate subjects into different groups. For binary outcomes, the ROC curve is commonly used for evaluating discrimination, which plots the sensitivity against y minus the specificity. A test statistics used here is the C statistics, which equals to the area under the ROC curve. So that's it for our presentation. To sum up, like here we conclude the following global multivariate modeling strategies. For the sake of time, we're not repeating ourselves. Yeah, thank you.
Thank you very much. So regarding this, how to say this prediction uncertainty or prediction interval question, there's some recent advance from machine learning called conformal learning, which aims to provide a prediction interval for each data point in the test data set, which is kind of related.
Yeah, we have that in the full paper.
Yeah, thank you.
Yeah,
Thank
you for mentioning that.
Thank you.
Thank
All
you.
right, thank you. And then next one, Davis.
Can you see my screen okay?
Yes.
Okay, cool. So today I'll be presenting on my project, which is the likelihood of community college bachelor's degree adoption, examining 3 logistic regression models. And so this is an application based off of 2 book chapters from the Harold Jr. book, so chapter 10 and 11. And it also integrates some of the stuff that we've learned this past quarter as well. And so in the past 2 decades, there's been a rise of community colleges that offer bachelor's degree programs. And this is the value proposition is like, it's supposed to take advantage of the financial and geographic accessibility of community colleges to help increase baccalaureate attainment in the US. And there's lots of early quantitative analysis to suggest that there's lots of positive academic and labor market outcomes related to students who participate in these programs. And then prior research has kind of highlighted that a community college's institutional characteristics, particularly their enrollment size or the racial composition of their college, are related to student outcomes. And so one of the things I was kind of curious about is, are there types of community colleges that are more likely to adopt this policy to offer bachelor's degree programs, and really thinking about perhaps policy implications for educational access and equity, particularly if these programs are meant to be innovative and the outcomes are good. And so I thought that given my research question, one way to perhaps address and generate insights into this is to use logistic regression and to think about P as a probability that a community college has adopted a bachelor's degree program as a function of a bunch of predictor variables. And there's 5 of interest that I'll be talking about and using throughout the 3 model formulations that I came up with. And they're informed by 1, domain knowledge, but 2, also some theoretical and empirical work previously. And so the five predictor variables that are included in the various models is percentage of Black students enrolled at the college, the percentage of Latin students enrolled at the college, the total enrollment size, whether the community college is in Florida, and then whether the community college is in Washington. And I have Florida and Washington just because they have pretty mass adoption of this program in their respective states, where the majority, if not close to all their colleges now offer a bachelor's degree program. And so the data set that I used was web scraped, as well as merging across different data sets from the Community College Research Center, which is to get the list of public community colleges, which is surprisingly hard to get, as well as a listing of all the community colleges nationally that have adopted this policy, which is about 19%. And then IPEDS, which is a national data set that has various enrollment characteristics data that we'll be using for my model. And so I ended up having to remove 4 community colleges just because there was missing data for the predictor variables. And then just to improve predictive power, I ended up scaling the predictor variables at mean 0 and standard deviation 1. And so there's 3 model specifications that I developed for this project. The first one is similar to kind of what I've highlighted, which is the enrollment characteristics, the racial composition, and then the state to which the colleges were at. When I was looking at the partial residuals, it looked like there was lots of potentially nonlinear relationships or nonlinear relationships. So I ended up just developing a second model that just does interaction terms across these 5 predictor variables, with the exception of Florida crossed by Washington, just because they were both binary variables. And then I developed the third model from using a bootstrap validation technique that was mentioned in chapter 10, where it helped with parameter selection. And through the first 2 models, it kept on removing Florida as a predictor variable. So I tried out model 3 and kind of went through the process of what was outlined in those 2 chapters. And so this is kind of some of the estimates and the p-values in relation to each of the models. Model 1, we can kind of see that total enrollment size, the percentage of Black students enrolled, and whether the community colleges in Washington had statistically significant effects at a 0.05 alpha threshold. For model 2, we see that none of the interaction terms were statistically significant, but again, we see total enrollment size as well as the percentage of Black students enrolled, and then to a lesser degree, Washington. For model 3, interestingly, some similar results where total enrollment size in Washington pops up again, and then the percentage of Black and Latin students to a lesser extent. And so I kind of went through all the diagnostics that we've been going through in class, as well as in the book, just to look to see perhaps some influential points. So I plotted the Pearson residuals against fitted values, and you can kind of see some potentially influential points. And then some leverage values as well across the 3 models. We see some potential outliers and highly influential observations in the data set. But then when I calculated Cook's distance, none of them seem to be empirically influential. And then to quantify predictive abilities, I took 2 different techniques to calculate quote unquote pseudo R-squared, which was the generalized Najo-Kirk. We see that for models 1 and 2, they seem to perform better using that metric, as well as in the Medalla-Cox-Snell metric as well. And then I used bootstrap validation of 150 resamples. And I'm just going to show you model 1, and we can kind of see, I want to highlight just the discriminant index of 0.60, which is modest but decent, and then some consistent R-squareds as well through the bootstrap validation. And I think this kind of confirms my general thought, was just that for simplicity's sake, model 1 seems to perform the best out of the 3 models, just given the complexity of model 2, And then the lack of inclusion of Florida in Model 3 just seems a little strange from the domain knowledge side of things. And so these are some of the consistent results that I kind of highlighted across the three models, just positive relationships, policy adoption among enrollment size and whether the state is in Washington, whether the college is in Washington, and then a negative relationship of Black students enrolled at the college. Some future directions would just be to consider time effects. So the data that I drew was based off of 1 year. And so it's very possible that enrollment might have shifted over time as colleges adopted these policies. I could also use different outcome variables. So instead of going binary, I could just count how many programs that colleges actually have, and then evaluating different prediction error rates. And then as these programs become larger, just thinking about potential states to include or exclude from the models that we use. That's it.
So Davis, this is very interesting. The only thing I want to point out is that this seems to be not aligned with the scope as a review paper. It seems to be your project.
Yeah, I thought one of the on the syllabus, the final project, I think there was 3 options. One was applications of generalized linear models.
Right, but for
the
that, I
second
still
topic.
meant to review other people's application papers instead of proposing your project. But given that it's actually close to the timeline, and I just realized this is what you did, maybe you can clarify whether you did this specific for this class, or it's for your master's thesis, or is it for your PhD research?
It's related to PhD research, but I hadn't developed any of these models prior to this class.
So at this time, my suggestion would be try to add some literature review to this project, to your report, about what has been done before, right? What is like the new question you try to answer by this data analysis?
Okay. Yeah, I'll send you a message. I know, in the interest of time, I can send you
Sure.
a message.
Yeah, and also another thing I want to add is that I wonder why not studying this question within Washington, within the state, because it seems that this policy might be state specific.
There are about 24 states that have adopted this policy, and so
Okay.
in Washington, there's only about 18 community colleges, and
I
so
see.
I think the sample would be pretty small.
I see. Okay, thank you. So then let's move on to our next presenter, Andrea.
Yes, sorry. Just making sure everything's here. Yeah, I can share my screen.
Sure.
So, yeah, I can start. So what I focused on was on ordinal logistic regression. So basically what I covered was chapters 13 and 14. So it's mainly on ordinal regression, but I wanted to apply it on a different data set. So let's get started. So
Sure.
you probably know, in the very first presentation, you probably know regarding like ordinal variables and the like, and that basically what they are is like they are categorical response variables, but they have a very clear order or ranking involved in those. So you can see the difference between the nominal ones, which just describe what the value is, versus ordinal, where you can see if it's like good, bad, good, or excellent, or you didn't like it or you loved it. It can be discrete from the start, or it can be grouped from continuous variables, like how Lori's mentioned it. So the main question is, how do we determine the effect of the predictors based on this order or the ranking provided in the target variable? So that's where we have ordinal logistic regression. Basically what it involves is that it predicts an ordinal dependent variable just given any predictors and the like. So it is similar to multinomial logistic regression. However, what multinomial logistic regression does is that it just identifies multiple variables, but it removes the order in the process. Ordinal logistic regression does not do that whatsoever. They maintain the order throughout, for example, through this clustering and like. So there is some assumptions required for this, particularly like ordinality, which basically checks to maintain the order, as well as proportional odds assumptions, which as mentioned before, is making sure that the log odds of each cutoff basically apply across the levels. So there are two models that focus in on sorry, there are two models that focus in on handling ordinal logistic regression, especially regarding discrete target variables. So the one is the proportional odds model, which basically focuses on cumulative probabilities. So there are two ways to handle this. One is where we want to see if there is k-1 cutoffs for k levels, and if y is less than or equal to cutoff j, then it would be represented as the top left over here. If we want to focus more on the another way to do so is if we want to focus on the what is greater than or equal to the cutoff. That's when you can use the one on the right. So basically, response y can be continuous. This is just one case where response y can be continuous, or in this case, it could just also be discrete, and then j just represents the value itself. Basically, we'll check the cumulative probabilities and the probabilities from the logit of each cutoff, where we have, for this case of the logit, we have alpha as the intercept, and beta is basically a constant slope of regression coefficients. So for the proportional odds assumption, the key thing for a proportional odds assumption is that it focuses on logistic regression, both the log odds, and basically we want to make sure that whoops, that wasn't supposed to be there. We basically want to make sure that the target variable is linearly related to each x. So we do want to treat each level. We can treat each level sort of as like a binary logistic model in this case. But that is only one model in this for this. The next one we want to we can focus on is the continuation ratio model, which focuses more on the conditional probabilities instead of just like the cumulative ones for this case. So once again, it really depends on if you want to use the backwards continuation ratio or the forward one. So for the backwards one, it will be based on like if we want to focus on level J, given the condition, given what we know about what it is under J, or if we want to focus on what is over J for this case. So it really depends. It depends on if you want to go forward with this, which R usually focuses on, or if you want to handle the backwards approach. Either way is dependent on the context. So it does focus on a logic where we want to focus on the probability, the log odds of being in level J versus below level J, or for the forward case, it could be whether it's in level J versus above J. So we do treat this as a series of binary logistic models, and to handle analyzing and fitting this model, we do use something like partial residuals. There are some assumptions that we still need to keep in mind, especially considering constant slopes. However, to make this more lenient, that's when we use an extended continuation ratio model, which basically allows for non-constant slopes for various predictors. Now, when it comes to applying this, what I did was I wanted to see how it could handle where it handles non-ordinal variables, but it's still labeled as such, basically. So what I did was use the UC Irvine's wine data set, where it has a chemical analysis of 178 wines from the same region in Italy. What their response, basically what it is that they analyze the chemical analysis. They are from the same regions, but the main difference is that they're grouped into 3 classes where it just represents the way it's cultivated, a different wine class or type. So supposedly it's labeled as an ordinal variable, and that is listed as type 1, type 2, or type 3. But there's no inherent order. We want to see how well it can determine how well we can apply ordinal regression, though, seeing if it can preserve the order based on the info we're given. Based on the 13 predictors and characteristics, which are mostly like on chemical properties or color or appearance. So we have the ordinality assessment to determine all of this, and we find that a good portion of them do satisfy this, especially the case with alkalinity, phenol-based variables, as well as like hue. It has a little bit of a inconsistent slope, but this we'll use more later. But yes, we do see a case of satisfying the ordinality assumption for a good portion of these. The rest can be a little bit tricky in regards to explaining it in terms of like an unordered class or just nonlinear predictors and such. The phenol-based variables do have the strongest match in regards to the proportional odds and the continuation ratios constant slope assumption, especially with how well they can match. They tend to match the stratified means based on this assessment. Any variables that have significant collinearity, such as color intensity or total phenols, were ignored so that it could have a stronger model in this case. So now we have the proportional odds application where we try to see if we can apply this here. So first we want to see if I can apply this to as much as all of this as possible. And this was still being tested back when as it is, but I did try to incorporate Ash later on. But for this one at least, we want to see like how well it could handle proportional odds, how well the proportional odds model could handle this. So it did fairly match how the assumption was satisfied with regards to proportionality as well as ordinality as well as proportional odds for this case. So we do see like most of these do have a fairly proportional rather parallel slope to an extent. The main the main offenders, however, seem to be stuff like malic acid or magnesium in this case, where you do see like really inconsistent nonlinear issues with this. That can be probably attributed, though for magnesium, you can see that there is a noteworthy cutoff where we can see that it can predict something like where it's from the third wine class 3 for this case. So even if there is nonlinearity, you can see that it may be good at predicting a particular level for this or particular class for this. But this still matches with the wall test where we see like how significant or how important each variable each predictor can be for this. However, since this is inconsistent across predictors, that's why it may be more useful to assess the conditional odds, the continuation ratio model for this. So that's why we did want to use the extended CR model, and we wanted to have a condition. We incorporate the cohort or the condition that y is greater than or equal to j, at least for this forward continuation ratio model. So obviously we cannot incorporate all the interactions or all of the terms for this because it could lead to too much complications for the model, which is why I added a penalty, particularly of like for simple 0.05 for simple terms and an interaction for 125 for simple terms, as well as like interactions. Though what I did note was that even though even though the cohort level or class level was significant, the interactions do not show as much improvements when being incorporated. This could be just from the wine type order. There are multiple factors that could be confounding this as well, but it could be just from a case of like a cohort by cohort basis. So that's why like the final model at least focuses on like, this is based on all of the models for predicting that the wine type or wine class is equal to the first one in this case. So that's why we have like a variety of these. It seems to, this was mostly the best I can extract, though I will analyze this more at least after this. It's sort of a case of sort of time constraints and such, but it is a little bit tricky, especially with such a small data set. As for analysis with this, what I did was apply like a bootstrap calibration to see how well it could fit with the actual probabilities versus the predicted probabilities. And we see that the mean absolute error is like 0.021 in this case. So what I did was with the apparent one and the bias corrected, like the overfitting corrected calibration, we do see sort of a nonlinear estimate, which tends to predict lower invalidation, but it still tries its best to at least match itself to an extent, especially with the higher probabilities when predicting when the wine type is the first one in particular. This can expand. This could be extended further to the other two wine classes in this case. So as in conclusion, we see like at least for discrete ordinal variables, we can see that the extended CR model, continuation ratio model usually is the better one, especially given its leniency to handle proportional odds assumptions as well as varied slopes. It can be inconsistent at times though. This may be just attributed to, once again, limited data, or how the small data set is, because there's only like 178 wines compared to needing more data in this case. The graphical methods provided, such as determining like partial residuals, a goodness of fit, the calibration models, those have been effective to at least determine how well the models can fit it and see how we can improve the regression model from there. It may be effective at maintaining order from like these. It has a potential to maintain order from these unordered variables, sort of like ranking 3 wines from a wine tasting contest in this case. But future analysis, I do want to see how I can test more with on penalization, see if we can find a better model for this, as well as filtering variables, because there were cases where, like seeing how like removing the insignificant ones like magnesium or malic acid could improve ordinal predictions from there. But yes, most of this was just me testing out, seeing how well it can apply it to there compared to how the textbook case study was. So yeah, that is my work so far.
Thank you, Andrea. Yeah, my comment is similar to mine, the ones I gave to Davis. I think this is more like an analysis project, and so therefore I'm very curious, because this UCI one dataset is a classical one. I know UCI has this dataset for machine learning, where I think you need to check what has been studied on this dataset before, like a review of what has been done on this dataset. That's my suggestion. Yeah, thank you. Thank you for the presentation. So let's take a 10-minute break for now, then we will resume, because I just need to finish something right here. And let's pause for now for 10 minutes, then we'll come back with Han and Shirley and Graham and the previous group. Thank you. I'll resume the recording.
Hello, do you see your screen?
Yes, very well.
Okay, cool. Hello, we're Han and Shirley, and we'll be presenting on modeling longitudinal responses using generalized least squares. Just an overview. First, we're going to talk about some background information, and then we're going to talk about the model setup, and then model validity, and then finally the model evaluation.
So first we'll talk about the background. So first, what is longitudinal data? We say that a data set is longitudinal if it tracks the same type of information on the same subjects at multiple points in time. So in this plot here, we see that each line represents a subject, and it's taking repeated measurements of blood drug level over the course of time. And why are we interested in studying longitudinal data? So on many topics, longitudinal studies typically contain far more detailed information than could be collected through a one-off survey. This is because we're just recording more information over time. And longitudinal data collection allows researchers to build up a more accurate and reliably ordered account of the key events and experiences in the participants' lives. And longitudinal studies have been shown to help reduce the impact of recall error or bias, which occurs when people forget or misremember events when asked about them later. So the running, oh, it's on the slide. Oh, sorry. So the running example we're going to be using in this presentation is the cervical dystonia dataset. This was a randomized control trial of the effectiveness of Botox and reducing pain for cervical dystonia patients, which is like muscle clumping in the neck, I believe. They tried 5,000 units, 10,000 units of Botox, and they had a placebo treatment group. And they measured something called the Twister score, which is essentially a measure of pain, where a higher score indicates a higher pain level. So this is what the data set looks like. You can see that there's repeated measurements of the Twister score in the far right column, taken over weeks 2, 4, 8, 12, and 16. The first 5 rows shows the first subject, the next 5 show the second subject, and this is just to show what a longitudinal data set would look like. And this is how they plot longitudinal data sets. So in the left, we have subjects in different colors split by their testing site and treatment. And this is measuring the Twister score over 16 weeks. And in the right plot, we have the average Twister score across the different treatment types. And here we can kind of already see that for the two Botox treatment groups, we see a dip first, which might indicate a slight effectiveness in treatment, but it starts to go away over time.
All right, next I'm going to talk about the model setup. So first, we're going to talk about the effects on the expectation. We modeled the expected value using the equation on this slide. Then the expected response of subject I at time t is represented by y of it, and it depends on xi, which is the covariate of subject I. We also modeled the time trend with k parameters as shown here. And then the basis function for modeling the time effects are given by g1 to gkt with parameters gamma 1 to gamma k. And then some common basis functions are k dummy variables for k plus 1 unique times. There's also k, if k equals 1, that's just a linear time trend. So then g of t is just equal to t. You can also do a k order polynomial, or you could do a k plus 1 not restricted cubic spline with one linear term and then k minus 1 non-linear terms. And then for the data setup, the first response measured at time t I0 is typically a covariate in xi, and we use this first response as a baseline for that subject. And the rest of the data is arranged in a tall and thin layout to allow for irregular time measurements. So if someone came only on like weeks 2, 4, and 8, but not 16, they can still be part of the data set. Next, we're going to talk about the generalized least squares model. So in typical OLS, we assume that the variance of epsilon is equal to sigma squared times the identity matrix. But in GLS, we assume that the residuals are correlated in some way. And this means that instead of the identity matrix, we use a matrix called sigma. And then beta is now estimated by this equation. And since there's some dependencies within the data due to same subject having multiple responses, we have to use GLS to capture that correlation. Here are some common correlation structures that R provides in the NLME packet. We can see that we're using isotropic correlation structures. So that assumes that correlation between responses within subjects at 2 times depend only on the measure of distance between the 2 times, not the individual times. So that's like shown at this absolute value of T1 minus T2. Yeah. And then here's an example of a GLS call. So we're setting the twister score as the response, and then we have all of our different features. So we had treat, and that is the treatment like 5,000 versus 10,000 versus placebo, and that is interacting with the time, and the time is represented by a restricted cubic spline. And then we also have the baseline, which is also a restricted cubic spline, and then we also have the age, which is interacting with the sex. And then the correlation that we decided to use is called COR1, just because it had the lowest AIC score when we try the different correlation structures. And then the form is weak by UID because the correlation is between the UIDs.
So next, we'll talk about how to check the validity of the model when modeling for longitudinal data. So first, we check the validity of the correlation pattern by plotting a variogram. So in our running example, the variogram will plot how much 2 samples taken from a subject will vary in the twister score as a function of the time between those samples. So in other words, it looks at how much 2 samples would vary over time by estimating the correlations of all the possible pairs of residuals at different time points. And here the plotted points show the measurements of the actual data points, and the line represents the modeled function. As they follow a similar curve, except at week 4, you can be pretty confident about the choice for the function used to model the correlation. And we can also further verify the validity of the model with more standard approaches by checking the residual plots and the QQ plots. The residual plots show the constant variance assumption, and the QQ plot on the bottom right helps us check the univariate normality assumption.
Okay, and then finally, we're gonna talk about the evaluation of the model. So first, we have a plot of the ANOVA of our GLS model. We can see that the baseline twister score has a very high effect on the responses, which makes sense since it's the starting value of all the subjects, like initial Twister score, initial pain at week 0. And then after that, we can see that week treatment and then treatment interacting with week have relatively high significance as well, which tells us that those are probably affecting the subjects in some way. And then finally, age, the interaction with age and sex don't have much significance on the effect at all, which is good. And then here we have a comparison between low dose to placebo. So this is 5,000 units to placebo versus 10,000 units to placebo. And in both cases, they start relatively low. So that means the low dose is actually helping with the pain. But then as we can see around week 12, it's starting to get closer to 0. And then by week 16, there's basically no difference at all. And then for the high dose, we see the same thing like in week 0 or weeks 2 to 4. There's a lot less pain. And then actually once we get to week 16, there's more pain. So this tells us that the treatment probably has effect early on, but the effects kind of wear off around weeks 12, and then the pain could actually worsen if you provide too high of a dosage. And yeah, thank you for listening.
Yeah, so may I ask why you chose this data set to analyze? Where did you find this data set?
It was provided by the text. So this is the data set that the textbook actually used for the case study.
Yeah.
And it's
I
a
see.
really good example of longitudinal data.
I see. Did you repeat the analysis in the chapter or you did something new?
We just repeated the analysis.
I see. So basically you showed that you could reproduce the results in the book.
Mm-hmm.
Did you try something more beyond what's in the book?
We weren't really sure how to, because this chapter just basically explains that like GLS can be used for longitudinal data. And then they go into the very detailed case study on how it can be applied and how you can evaluate if it's doing good or not. So we weren't sure what else to really add to what they already had.
That's the suggestion about this review or this final project report. What I hope to see is what you can think out of this box. For example, if you search for longitudinal data, what other analysis approaches are out there besides this GLS? Could you try that as a comparison? I think that means you are thinking beyond this chapter. And that's what I hope to see.
Okay, I think we just
Yeah.
weren't sure about the expectations of like what to go off of the chapter, but I think it's clear.
Yeah, but I'm not saying it's expectation. It's what you should expect for yourself. I'm not sure whether you are PhD students or master students. Could you tell me again?
We're masters in computer science.
Okay. Computer science, I see. Yeah, because what I'm suggesting is how basically it's a way for you to do the learning in an active way. So what I'm thinking is that trying to find pieces of information and try to unify them in your own way, that's where innovation happens. That's my suggestion. So that's why I wouldn't want to say it's an expectation because I want to make this open-ended.
Okay.
Yeah. But if you don't have enough time, that's fine. But if you still have some time, it will be interesting to see what another approach would work. Well, would it give you different conclusions?
Okay.
Okay,
Yeah.
we'll look into that. Right. Thank you.
Yeah, thank you. All right. So Graham, you are next.
Okay, great. Can you all hear me okay?
Yes.
Okay, here we go. I'm gonna share. So today I'm going to be talking about hierarchical models in political science. That's what my review piece is on. And this is not a photo of me. This is a photo of statistics and political science professor Andrew Gelman at Columbia, whose work I'm going to be talking about today. He is definitely the most sort of prominent political scientist using multi-level, as he calls them, or hierarchical, as we called them, models in political science. So just to kind of get us into this, and I know it's been a long day of presentation, so mine will hopefully be a little lighter. So just paradox between wealthy states and wealthy voters. So if I asked you, do you think wealthier states in the United States are more likely to be Democratic or Republican? What would you say? People were a little bit confused about this when he was writing in 2007, 2008, and they thought, oh, well, wealthy people, they're more likely to be Republican, so wealthy states would probably be Republican. That would be wrong. Wealthier states like California and New York and Connecticut actually consistently vote for the Democrats, and poorer states like Oklahoma or Mississippi vote for Republicans. But if you look at individuals, if you have individual level data, wealthier people are more likely to be Republicans, and poorer people are more likely to be Democrats. So there's this big paradox. Gelman sees a lot of journalists saying things that he thinks is not are nonsensical claims. And so this sort of the breakthrough of this piece is like, you need to have varying intercepts, essentially. And so instead of doing a classical regression where you just look at the individual level data, we'll get into that in a second, or just look at the state level data, because those will contradict each other. So if you have the median income of the state, and then you have the vote share, those are the dark circles, the dark black circles on these graphs, right? You just have the median income in the state and the vote share in the state. You're going to see, as you move to the right and get wealthier, less support for Republicans. But looking at individual level data in a multi-level model where there's this hierarchy of people inside states, and allowing states to have different baseline levels of support, you see that a state like Mississippi is different from a state like Connecticut in that it's overall going for Republicans more, but it's a poorer state because more of the people in Mississippi are at the lower end of the income distribution. So this is split into quintiles here. So this is very 2007, 2008 R graphic, but you can see like the lowest quintile of income is bigger for Mississippi than in Connecticut, where you have more wealthy people. So this is huge. He allows the slopes to vary too. This is exactly what we were talking about towards the end of our course. And the claim in this piece is that for poorer states, the relationship between income and vote choice is stronger. So the idea is that in a wealthier state like Connecticut, it's going to be flatter, which you see on the left-hand panel in 2000 for the George Bush election. But he's really like squaring these two claims that journalists and political scientists alike were confused about with individual level data versus state level data. So having the model account for that hierarchy was really important, because that's the like true data generating process. So I know for us, it just sounds like, oh, you fit a multi-level model, you fit a hierarchical model, but like this was big in political science when it came out. So I revisited this concept with a slightly different data set in past few weeks for this project. And here I'm just going to plot the poorest 5 states and the wealthiest 5 states. And this is the graph of the people inside the states. So again, it's not the median income state relationship where I have 51, including DC data points. Each one of these is just a bin of voters in our national voter file where we observe their income somehow. I'm not going to get into that right now, but in a row, we have income, the state that they live in. So we also know the median income of the state, and then which party they're registered with. So this is slightly different in that it's not vote choice, it's party registration, but you kind of see the pattern that Gelman identifies where like for the poorer states, maybe they're a little steeper on average. So this isn't the actual model fit, but this is just the bin data display. So the red state, blue state, rich state, poor state is a paper that came out in 2007. There was a book around 2008. So this made a lot of noise. And then the second thing I want to talk to, the second sort of like hierarchical models in political science concept I want to talk to you about today is multi-level regression and post-stratification, or Mr. P, as political scientists like to call it. So maybe folks have heard of this or it's used in other fields, but the idea is simple. It's like, say we survey 3,500 people in the country, but we want to really accurately estimate state level public opinion. So in my survey, I only have 3 respondents from Hawaii, okay? And I want to understand how my outcome of interest, like it might be affected by age, income, race, and other standard demographics. So with only 3 people in Hawaii, how am I possibly going to understand like how all those variables operate in Hawaii? Well, the idea is to borrow strength from the rest of the survey. A lot of these models will be fit using Bayesian methods, but all of the concepts could just as well be, you could fit the models with maximum likelihood. So yeah, imagine like you want to understand you're polling who's going to win the election, Trump or Biden, but you fit a multi-level hierarchical model where you have you might have an effect just at the individual level with no hierarchy, like with no group structure, like sex. But then you want to fit the age, you want to have age have a separate intercept within every state. For instance, you could set up your design matrix like that. Now, the post-stratification is just, oh, sorry for the typo there. Post-stratification is just a fancy way of saying you fit that model, and then for every cell, so once you have effect, like coefficients for white, age 18 to 29, state Alabama, go look at every cell in your data, and maybe it gets really big, 3,000 different cells for state, race, income, age, predict the probability based on your generalized linear model for that cell, and then take a weighted average in the state or locality of interest based on how many people of that type are in that state. So you get a probability that a white man aged 18 in Alabama votes for Trump, and then you weigh that to get the full estimate of Alabama. Now, here's just a quick example of multi-level regression and post-stratification, where researchers wanted to understand the difference between people's preferences for the minimum wage in a state and then the state's actual minimum wage. So like here, California and Massachusetts want a really high minimum wage, and they have a high minimum wage, but you can see across the board that the preference in California at the time of writing was for a $12 minimum wage, and then the actual state minimum wage was closer to 10. So the claim of this paper is like, even though like policy is not actually reflective of what people want. You can't ask every single person in the country what they want the minimum wage to be, but you can take a poll and then use MRP to do better at getting opinion right in various geographies. Thanks, everyone.
Thanks. Did they compare this with other models, like simpler models, to justify this level of complexity is needed?
They did, yeah. They compare with like various pooling strategies, and compare with just the raw, like take the raw average of what you have in your data. And they showed that it does better. You have to choose a situation where you can validate. So like if you survey 3,500 people for what they think about the election, they use the outcome as the true vote share come election day. So it's like, that's a sort of cheeky way to validate it. But yeah, I was wondering if this method is called something else in other fields, or or if other fields have to deal with the same problem.
Yeah, and did they do some sensitivity analysis to show how robust the results are, the conclusions are?
In the initial paper, no. It's in a journal called Political Analysis. But I think folks have extended it to do multi-level regression and post-stratification over time. So like you want to understand, so this ties into the longitudinal data that we heard about from the last group. It gets a lot more complicated if you want to think about different periods in time as opposed to one snapshot. And I think that the research there is more rigorous, and like there's been more sensitivity analysis done. Do you mean like for emitted variable bias in these? Yeah, that would be a good idea. Maybe I should do that.
Yeah. Okay. Thank
Thanks.
you. Thank you. Yeah, it's very interesting. So our last presentation will be from our original group 3. Please go ahead. Are you muted?
Yeah, I'm sorry, madam.
Okay.
Hello, everyone. Thank you, Professor, for giving us permission to go at the end and change our order. I am a PhD student at Anderson, and my motivation to take this course is to understand the empirical research done in management. Even though I'm myself not an empiricist, but we come across job talks and seminars in which people use data to understand different phenomena in business. So in my final review, I want to see how linear models are applied in business context and specifically in the context of retail. So I'll be presenting the first paper from one of our seminal works in this field, and I'll go through the motivation, hypothesis, data, and then model and how to interpret the results of that model. And then my colleague will do it for the other paper from a other top-tier journal. So retail companies invest heavily into advertising. Like in one of the years, it has been up to like 17 billion. But all advertising does is bring people will bring people into the shop. But it is what really companies care about is the money they generate. So it is important for us to understand how does the footfall in the shop convert into sales. Like this relation between traffic and sales is very important for them to have strategic advertising decisions. And similarly, we want to understand and the second most money consuming thing in retail world is the labor. And we want to effectively manage labor. For that, we need to understand how does labor influence this conversion of footfall into sales. And also, if like the conversion rate, which is the number of people who walk into the store actually ending up buying, this also influences the future incoming of those people, like customer loyalty. And if we understand how is labor influencing all of these, then we can also have long-term strategies instead of just thinking myopic. So the paper defines all of these questions more formally, as the hypothesis one says that the relationship between traffic and store sale performance is increasing concave. And the rationale to come up with this hypothesis is maybe like with increase in footfall, we expect more chances of more people end up buying stuff. But we should also make sure that with more crowd in the store, the service level would decrease. Hence, people would not have enough information or enough time to check out, and hence they might drop down. So hence we expect a concave kind of a curve. And then using data, we try to support this hypothesis. And then second is the greater the level of store level, the greater the positive impact of store traffic on sales performance. And as I just told, the larger the sales people, the better service quality you can give to the customers, and hence you can hence the conversion ratio would improve. And the third hypothesis is about the variability. Part A is within a day, if the variability of my demand is fluctuating, then it will be difficult for me to adjust my labor. So mornings or evenings, like depending on the time of the day and the schedule of the laborers, there would be times in which the mismatch might happen. And because of that, again, the quality of service would reduce, hence the sales would reduce, even though the footfall increases. So 3 and 3B are for interday and intraday variability of traffic, and how is that affecting the sales performance. And finally, we try to see how does increased traffic relate to conversion rate, and also how does conversion rate affect the future incoming of customers. So they collect data set from an apparel store in Europe, and they collect it from 41 different stores, and they measure all of these attributes. So the independent variables in their study, like a few of them here are listed, and each variable has an average, which is the average over the number of hours in a day. So each variable, if it is prefixed with A, it is the per hour value of the corresponding variable. And the important variables here are the labor and the traffic and the variation, which is also quantified as mismatch between labor and the traffic. And the dependent variables are it's the sales, it's the conversion rate, and it's the basket value, which is the total value divided by total sales happening, which is how much is each customer spending. And also the traffic in future periods. And the control variables are like temperature, income, demographics, and the economic condition of market. So our first model is a simple linear model in which there are a bunch of all these variables. But for us to answer the hypothesis 1, we just look at the coefficients of the first two variables, gamma, mu1 and mu2. And this shows like there is a square term which indicates the concavity or convexity of the function, which is like it being significant would mu2 being significant would imply that it is not a linear function, and mu2 being positive or negative would help us understand if it is concave increase or convex increase, given mu1 is positive. Similarly, hypothesis 2 is validated by the coefficients mu2 and mu3, and hypothesis 3 is which corresponds to the variability is defined by mu5. And hypothesis 2, to remind you guys, is the effect of labor on this increase between traffic and sales. That is why we try to understand the coefficient of the cross terms. And here in this, mu1 represents the fixed effects of each store. So each store can be at different geographies, which would correspond to different demographics, and also sizes, and also the managers and the skill level of the laborers, which would all have an effect on the sales. And WIT is the it's column bunch of controls like, and all of these variables are time dependent variables, but mu the store effect is again a linear function of other variables that are time independent. And here the Z1 variables are control variables, and the gamma 2 corresponds to the variable of intraday traffic variability. And the interpretation of results is this big table. So like as we discussed in class, the model starts off with just the control variables without adding any of the variables of our interest. So model 1 has none of these starting variables, which are really interested to us. Then with each model, we keep increasing the variables, like adding the variables to our model and see if it has any effect on our dependent variable. So in model 2, to our control variables, we add the traffic linear term and traffic quadratic term. And we see that the significant result is that both the coefficients are significant, and the linear term is positive and the quadratic term is negative, which says that it is a concave. Like beyond a point, increasing traffic doesn't really help us in sales. And in model 3, we add the cross terms with labor, and even these results are significant. And in model 4, we add the intra variability, and we see that variability is not good for our sales because there is a negative coefficient which is significant. And then we remove the intra variability and we add the mismatch of labor to the demand. And even here we see that there is a mismatch. And here, if we come down, we can also see how competition has a negative effect, and how APCI is the average per capita income, which has a positive effect on our sales. Like basically, and also the labor, which are these two rows, also have a diminishing returns, which are concave, which have a concave effect on the sales. What I really wanted to understand by taking this course is to understand these tables, because initially when I used to read these papers, it would be really difficult for me to understand what is these tables or how to interpret it or what are they exactly doing. But now I think I kind of understand it better. And now they have one more result, which is now they changed the dependent variable. Instead of just the sales, now they have conversion rate as model 6 and model 7 as average transactions per hour. And then 8 is the basket value, average basket value. And then they have similar results. And like It is the same thing. They apply linear regression and they try to interpret the coefficients. And now my colleague will discuss the other paper in detail.
Hi everyone, this is Vaibhav. Now I'll talk about the impact of weather fluctuations on the retail sale. So I'll be discussing a paper by Victor and Abdel, which was published in European Journal of Operational Research in 2020. Nareen, can you go to the next slide? Yeah, so in this paper, the author based the retail sales on two major decisions. The first one is customer deciding to go to the store. And it depends on the factors such as cost and weather. And the second decision is once the customer is at the store, then whether he or she decides to purchase an item, and it's driven by store variables such as the variety available as well as the promotions available. And so in this paper, the focus is to identify the impact of different weather variables on the customer's decision with respect to whether he wants to visit a store and purchase an item. So the authors propose a couple of hypotheses. The author proposed a couple of hypotheses. The first one is that the rain increases footfall on shopping center stores and decreases it in street stores. The second hypothesis is divided into two parts. The first is that for a given historic absolute temperature, the temperature decreases footfall. And secondly, that the effect of temperature footfall is more negative when the historic temperature is very low. And on the conversion front, which is defined as the probability that a customer buys a product, is that the sales of summer clothing increases with higher temperature deviation. And the last two hypothesis talks about the discount sensitivity on rain and temperature. Regarding the data set, so the authors collected the data from large apparel retailers in Europe, and they focused on 98 stores, out of which 41 were on street and 51 were in shopping center. Nareen, can you go back to previous slide? Yeah, and the weather data is collected. Is there a question? Hello?
I think one of you need, Noreen, you need to be muted because there's like an echo. I don't know why.
Nareen, can you mute yourself?
Yeah, I just muted him. Maybe you can continue. Okay, I think it's good.
But yeah, I don't see the screen because he was sharing the screen.
Okay.
Yeah, I see the screen.
Can you go full screen? All right.
Yeah, okay, great. So yeah, I'll just continue from this slide. So the author collected data from a large apparel retailer in Europe, which focuses on 98 stores, out of which 41 stores were on street and 57 stores were in shopping centers. And they categorized the product into two categories: summer products and winter products. And the weather data is collected from online weather underground resource. Nareen, next slide. Yeah, so this is the to study the impact on footfall, they used a reduced form of log linear model. Over here, NST is the number of visits to this store, to a particular store S in a given time period T. And you will see the independent variable XST, which is the seasonality factor for a particular store S in a given time period T. Similarly, DST is the average price discount. W is the set of weather variables which we are interested in. And since they have a large number of seasonality control, they are using a log difference model. Yeah, so this is the table which nicely summarizes their results. So F1 shows, if you look at the F1 column, it shows that rain significantly impacts the footfall. So for the shops which are on street, the number is negative, which shows that the footfall, so when it rains, the footfall decreases for the store which are on the street by about 7%, whereas the footfall increases for the store which are in malls by about 5.5%. And similarly for temperature generally has a negative impact on the footfall by about 0.0104%, but this is moderated by the historical temperature, and it is milder during the winter season, and the value is 0.000501. Nareen? Yeah, so this slide again sort of like summarizes the results which I just explained, that if it rains, then the footfall decreases for the stores which are on street, and it increases for the stores which are in shopping malls. So it's in line with the hypothesis one proposed earlier, as well as that temperature generally has a negative effect And if we include the historic temperature, then if the historic temperature is below 20 degrees, then the footfall decreases with temperature, as well as if it's above 20 degrees, then the footfall increases with temperature, which is in line with the second hypothesis, which was divided into two parts. To study the impact on sales, they again use the same reduced form of log linear model. Over here, new variable J is the category, and they are using the difference of log model. And they studied this model on two apparel categories: summer product, which is categorized as dress, and winter product, which are categorized as coats. And again, this table summarizes their results. So if you look at the first red box, you'll see two columns, C0, C1. C0 is their model without accounting for the weather variables, and C1 is their model accounting for the weather variables. So you'll notice that the weather doesn't weather coefficient doesn't have a significant impact on the conversion. So this again proves that that weather has this again proves that weather has a very weaker correlation when it comes to conversion decisions. And if you look at the so they simplify the model C1 into C1b because weather coefficients weren't very significant. So if you look at the two C1b columns for dress and coats, you will notice that that the rain doesn't have a is not very significant when it comes to impacting the sales, whereas the temperature is very significant, and which is in line with the hypothesis 3. And for the hypothesis 4 and 5, which talks about the discount sensitivity on temperature and rain. So if you look at the row rain times discount and temperature times discount, you will notice that these values are not significant, which basically invalidates the last two hypotheses. So yeah, this was the study which I wanted to show. So thank you. If you have any questions, please ask.
Thank you both. There is one question, I think, for Narin's part from Yingshi in the chat box. I think she was asking about the table. Whether the table in the first part, does the table contain p-values or coefficients? And Narin, you are muted.
I'm sorry. Yeah, I think all of them are significant at 0.01. Even though I understand the concern that the values are too small, but they are significant. They did mention it in the paper that these things are significant.
Right, because the values, the coefficients will depend on the unit of your covariates. Like, what is the unit? Because basically, the meaning of the coefficient is that if you change one unit of the covariate value, how much do you change the expectation of your y, right? So the unit matters. Yeah. Okay. Yeah, and also, how would you two want to unify the two parts into one paper? Because I think each of you talk about one data set.
Yeah, so my hope was that it would be like a survey paper in which we would survey different applications of linear models in retail, or like I wanted to actually check that with you if that would be fine. We also have other papers, but in interest of time, we didn't present it. But the whole reason I took this course is to understand and interpret the empirical work done in ops. So that is what I want to get better at the end of this course.
So for both data sets, did they consider anything like interactions of variables, interactions of covariates, or the clusters, right? Like the hierarchical linear model we talked in the end, the data may be like clustered. Do they have such consideration for the data sets?
In the paper that I presented, I did not see any clusters, but there was this cross terms, right, between labor and the sales, like labor and the traffic. If labor, what effect does labor have on the conversion of traffic to sales? Like that is the interaction term I found, but nothing apart from that.
Yeah. Okay, so yeah, I hope that because you two are working on one paper, I hope to see more connections or discussions between the two parts instead of presenting them as two separate analyses. That's what I hope.
Okay.
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 All right.
Thank you.
All right, I think this is the end of the presentation today. And thank you all for your presentations. And it's great to have to work with all of you in this quarter. I hope you find this class useful in some way for your research or for your future job. Okay, thank you. So,
Thank you,
thank
Question,
you.
Professor.
Yes.
Wait, question. So, is the limit supposed to be 5 pages or 6 pages with the final
I think
report? And how will you
I
be
think
grading this? Like, what are your standards, I guess, for our final report?
I would say the standard is more like the general standard for an academic paper, whether it's formatted well, whether you have the writing clear, whether you deliver something logical. That's what I would say.
Sounds good. Even if we may have
Yeah.
like even if our results may not be as optimal as we would like, it's still worth reporting as long as we can, explain and do so.
Exactly. Yeah, I would say whether it's clear or logical is the most important thing. For example, if I can read through your paper smoothly without wondering, oh, there's like a gap, why would you write this? Right? If I don't see those, it means that's a good paper. I think you should have your judgment.
I see. Great. Thanks.
Yeah.
Was it 6 pages or again, sorry. And are we allowed to include an appendix?
Sorry, appendix, you said?
Yeah, an appendix, or does it have to be like a hard limit, I guess? Like a 6-page limit.
I would say it's a hard limit. Yeah, it is a hard limit. Otherwise, if you have appendix, basically the page limit is not there.
I see. Okay. So 6 pages include the code as well?
No, I don't expect that. Because
Oh,
you wouldn't put the code in your paper, right? Nobody will put computer code in the research paper.
makes sense.
Yeah.
Thanks. Sorry,
And
was
I
just
also I have a quick question about the format wise. So is it okay if we use any format that's 12 size font and single space? Because the TA previously upload a template. I don't know if we're supposed to use that as a template.
Yeah, just use that as a template.
Oh, okay.
Yeah.
And since this project is more of a lit review, is it okay if we don't have like our original development of the topic, but just to like summarize and do some like case study based on what we learned from other sources? Like
So I didn't get this as a question. What is the question?
I guess. Would you be looking for like original novel development of this topic in our paper, or would it be sufficient to do like a literature review and maybe introduce different applications based on other sources that we've read?
I didn't expect this to be a new method, for sure. I didn't expect this to be a new method. I expect this to be a literature review.
Okay.
That's the original intention.
Okay, gotcha. And the last thing is that it seems like there's no submission link yet.
Oh yes, I will create a submission assignment on Brulearn so you can submit there.
Okay, thank you.
Okay, thank you. Okay, if that's all, for those of you who want to stay for questions, I will start the recording, by the way.